Okay, continuing now with the solution to the page 192 problem. This is similar to the problem that you did on your last test. You were going to figure out what the rent is and the security deposit is for an apartment based on the amounts paid by two different people. So the formula you use to do that is, and they give it to you here, although you could figure it out yourself, the cost of the apartment is equal to the number of months times the rent plus the security deposit. Remember, the security deposit is something you pay once at the beginning of the rental. So you don't pay every month. It doesn't matter how many months you rent it. The security deposit is always one security deposit. Now, for Ning, he rented the apartment for 6 months, so we put a 6 in for N, and he paid 35,000 SGD, so we put 35,000 Singapore dollars. So it's 6R plus S equals 35,000. We don't know what SR and S are yet, but if we have Ning's total and the number of months he stayed, and we have Tanushri's total and the amount of months he stayed, from the two of them together, we can figure out what the rent and the security deposit are, because there's only one combination of rent and security deposit which will make both of those possible. So like if you know one person's rent and the amount of time they stayed, it's not enough to figure out exactly what R and S are, but if you have two informations for two different people, then you would be able to figure it out. It's just like if you have 2 points on a graph, you can figure out a line. If you have two lines, you can figure out the point that they cross at. So, so here we have Ning's data here, and then we have Tanushri's data here. He stayed 24 months in the apartment, and he paid a total of 116,000. So now we have two equations and two unknowns. That means we can use the SMLT tool to figure it out, and we already have it in the right form. Now remember, to do poly-SMLT, we go to number 2 here, simultaneous equation solver, two equations, two unknowns. The rest of it we just leave the same. We press next, and now we just enter the numbers here. Which numbers do we enter? Well, we enter the coefficients, the leading numbers in front of each variable. So here it would be the 6. Here it would be the, there's nothing there. But remember, that doesn't mean it's 0. It means it's positive 1, because positive 1 times S would be S, so you don't change the value. So the coefficient here is 1, so we put 6 and 1. And then the coefficients here are 24 and 1, so we put 24 and 1. So those are the coefficients we're going to put on the left. On the right, we're going to put the constants 35,000 and 116,000. I'm going to pause the video while I enter that data in, because you already know how to do that. So the solution for the first variable, which we get by, we pressed solve there, let me do that over for you. We've put in our coefficients 6, 1, 24, 1. Remember, it's 6 times R plus 1 times S, 24 times R plus 1 times S, and the constant terms are 350,000 and 160,000. I'm sorry, it's 35,000 and 116,000. Then we press solve here, and it gives us the solution for two variables, x1 and x2, 45,000 and 8,000. Now, I'm not sure if I did that right. Okay, yeah, I was right. I had done it wrong the first time. So this is actually 4,500, not 45,000, and this is 8,000. So x1 and x2, these are the solutions for x1 and x2. Wait a second, my variables weren't x1 and x2. They were R and S. So which one is R and which one's S? Well, since I gave 6, the R coefficient first, since I gave 24, the R coefficient first, that means the first variable is R and the second variable is S. So if the first variable is R, that's x1, the answer is 4,500. The second variable is S, the answer is 8,000. So I already have my answers for R and S, and that is the end of that problem. Okay, now the next problems are going to be normal distribution problems. So the first one here is 6,000 people were asked how far they live from work. The distances were normally distributed with a mean of 4.5 kilometers and a standard deviation of 1.5 kilometers. Let's draw a picture of that just to start with. So we draw the normal distribution. The mean is 4.5 kilometers, so we put 4.5 right in the middle. Remember that a normal distribution, the middle is not only the mean, it's also the mode and the median. So all three of those central tendency characteristics are right at the middle of the normal distribution. And the standard deviation is 1.5 kilometers. So if we draw lines 1.5 to the left and 1.5 to the right, that is, you know, a majority of the people are within this region here from 3 to 6. Okay. Then it says find the percentage of people who live between 2 and 4 kilometers from work. Now that would be from here to here. So like between these two, what percentage would that be? Well, if I were just to eyeball it, I would say it's about 30%, but you know, that's just like making a guess. So let's figure out exactly. First thing we need to do is we need to figure out what numbers we're going to put in the calculator to figure that out. The calculator only needs a few numbers to figure it out. It needs the left and right boundaries you need, which are 2 and 4, and it also needs the mean and the standard deviation. Once it knows the mean and the standard deviation of the normal distribution, then it figures everything out by itself because it knows where it's centered and it knows how spread apart it is, so it can easily figure out the percentage. We figure out the percentage by using the function on the calculator for normal distribution. We access it by doing second distribution, and we're going to go to normal CDF, and we're going to put in 2 for the left boundary, 4 for the right boundary. 2, 4, and then we're going to put the mean 4.5, right? And the standard deviation is 1.5. And then we're already done. Paste, enter. And I had guessed about 30%. It's about 32%, 0.322. So it asks, find the percentage of people who live between 2 kilometers and 4 kilometers of work. I put 0.322 here. Actually, I should put 30. I should put 32.2%. Okay? Because they asked for percent, not for decimal. Find the expected number of people who live less than 1 kilometer from work. Okay, that would be this region here, right? So like this line here would be 1, and then everything to the left of that would be the percentage we want to find, or the expected number of people. So the first step to find the expected number of people is to find the percentage of people, and then we multiply it times the total number of people to get the expected number of people. So what are the boundaries here? Well, the left boundary is just negative infinity. The right boundary would be 1. So everything we're going to do exactly like we did before. So we'll do second distribution, except for now, instead of putting in 2 and 4, we're going to put negative infinity. And negative infinity in the calculator, you do -1 EE, which is this one here, and 99. So that's how you do negative infinity in the calculator. You put -1 times 10 to the 99th. So that is negative infinity. And then for the right boundary, we want to put 1, right? And the rest is the same because it's the same normal distribution. Mean of 4.5, standard deviation of 1.5. That's how spread apart it is. Then we go down to paste and we hit enter twice. And it gives us 0.0098, which is 0.981 or 982%. So that's the percent, but they didn't ask us for percent. What they asked for is expected number of people. So we're not even going to convert to percent. It's better to have decimal if we're going to do any kind of calculation after that. So we find the expected number of people by multiplying the total number of people times this decimal here. And the total number of people is 6,000. So I take 6,000, I multiply it times 0.00982, and that gives me 59. And so it actually gives me 58.9, but if I'm going to say the expected number of people on an IB exam, I would say, oh, I'm expecting 59 people, not 58.9, because, you know, people shouldn't be decimals. And then I'm going to do one more normal distribution problem, which we're going the opposite direction this time. This time, instead of figuring out where the boundaries are and then finding the percent, they're giving us the percent, and then we need to figure out where the boundaries are, where the boundaries are. And this is kind of tricky sometimes. In this problem, it's not so tricky, but I'll explain why. The weight of bags of tomatoes are normally distributed with a mean of 1.003 and a standard deviation of 0.02. So I draw a little picture. 1.03 is in the middle, 0.02 to the left, 1.01, that's one standard deviation to the left. One standard deviation to the right is 1.05. Okay. Find the percentage of bags that weigh more than 1 kilogram. Okay. It is known that 15% of the bags. Okay, find the percentage of bags that weigh more than 1 kilogram. And I haven't done that yet. I didn't see this part. So find the percentage of bags that weigh more than 1 kilogram. We're going to take, 1 here. Let's say 1's about there. Okay, and we're going to use the normal distribution function, which we get to by doing second distribution, and we're going to put the proper boundaries in. And it says find the number of bags that weigh more than 1 kilogram. The number of bags that weigh more than 1 kilogram would be 1 to the right, and so the lower boundary would be 1, and the upper boundary would be infinity. 1 EE 99, and this time we're using a different distribution, so we can't just leave the same 1 as last time. We need to put the new mean, which is 1.03, and we need to put the new standard deviation, which is 0.02, and then we do paste, and the answer is 0.933. Okay, so part A, the answer is 0.933, and the percentage, we need to multiply by 100 to get the percent. 93.3% is the percentage. And then it is known that 15% of the bags weigh less than p kilograms. So we'll draw a little picture. This red region is 15%. This boundary is p, but we don't know what p is yet. And there's a function on the calculator that figures that out. It's also in second distribution, and it's called inverse normal because it does the opposite of what we usually do with the normal distribution. We give it the area, 0.15, okay? And the thing about the inverse normal function is it always assumes that you're working with a distribution that looks like this, where the red part is on the left side, which is called a left-tailed distribution. If you have a right-tailed distribution, this doesn't work anymore, and we'll talk about how you adapt a right-tailed distribution into a left distribution to use this. But in this case, it's perfect because the calculator expects you to give it a region which like starts from negative infinity and ends here. Now, what if you have a distribution which is like right in the middle and it's like from 5 to 7 or something like that? What do you do with that? Well, the inverse normal function can't do that in one step. You're going to have to break it up. Okay, so in this case, we know that we want from negative infinity to p, so it's perfect. We give it 15%. Of course, you can't put 15 in here because it's expecting a decimal, not a percent. A lot of people make that mistake on the test. Give it 0.15 because it's times 0.01 or divided by 100. And the mean is going to be 1.03. And the sigma is going to be 0.02. And then we're going to paste that, and it's going to give us 1.009. So P in this case is 1.009. Okay? Now, what if it had said something like, it is known that 15% of the bags weigh more than P? Well, then you're talking about the opposite side, which would be this side, would weigh more than this P. And then you have a challenge because in this case the inverse normal function is expecting not this part, it's expecting like this green part here. Because it wants the left tail distribution, it doesn't want the right. So if you know that this red part is 15%, then the green part is what? It would be 100% minus 15%. It would be 85%, right? So then you trick the calculator by, instead of putting 0.15 in, you're going to put 0.85. So if I want to do the right side, then instead of putting 0.15, I would put 0.85, and it would think that I'm doing the green part, but I'm actually doing the red. And in the end, the boundary is the same. So that's how we trick the calculator into giving us the answer for the opposite side. So then this P would be 1.05. And you'll be able to see that it's actually symmetrical. The P on this side, 15%, is the same as the P on this side for 85%. Okay? So next video I will be doing the problem from page 243, which is a chi-square problem.